Good morning. Welcome to another chapter in our Monoxivent webinar series. My name is Brian Phipps. I'm one of the engineers here at Monoxivent. I'm joined today by Sam Stelzner, our other engineer, and our presenter today, Jim Wischhusen. He's the fiberglass division manager. He's been with us since 2010 and helps provide frontline support for sales reps and end users. A little bit of housekeeping before we get started in today's webinar. In the lower left corner, you will find a chat box, and we're encouraging participants to chat, text questions anytime during the presentation, and we'll be sure to get to them. Without further ado, I'll go ahead and turn it over to Jim.
Thank you, Brian, and good morning. My name is Jim Wischhusen, and I do run the fiberglass reinforced plastics division here at Monoxivent. And as most of you are all aware, Monoxivent FRP is available in above ground, below ground product lines, and the below ground is available in both single wall and double wall factory insulated. And we get this conversation going quite frequently regarding the insulated FRP, talking about R value, and from there the discussion turns into K factor and U factor, and it kind of gets muddied here. So we thought that we would present some basic information to everybody today, the facts as they stand, and where our product stands, and we shall go from there. Now, for all of you trivia buffs, you Jeopardy fans, there actually is a history for R value. So prior to 1945, engineers talked about U factor, and the U factor basically describes how much heat can pass through a given material. So the lower the U factor, obviously the higher the insulation value. Well, in 1945, it was presented that we can turn the inverse of that into a mathematical R value, and it caught on pretty quick because people found it easier to accept that the higher number, the better it is, and round numbers are also more appealing as well. So just a quick overview of some of these terms. R value is your resistance to heat flow, okay? Whereas your U value for a material is the actual amount of heat transmitted through that insulating material. Okay, and the relationship between these two is the U value is the inverse of R value. What's important to understand is that these definitions, these terms, all have units of measurements. They are absolutes. They are a material characteristic, and every material has their own U value and therefore R value. Along with this is also what's called K factor, okay? And as a sidebar to K factor or K value, you also have C value, which I did not want to include here only because it just muddies up the water. But the bottom line is that the K factor is the time rate of steady heat flow through a unit area of a homogeneous material induced by a unit temperature gradient. Big words, fancy description. Basically, it's saying that if you have a difference in temperature between two sides of material, heat is going to look to flow from the hot side to the cool side. And the K value describes how well this material will conduct through it. Now, the interesting part about this is that the K factor is not determined by thickness. The K factor for a material 1/8 thick is the same as it is for a material that's 1 inch thick. It's just a small little fact. When you start to talk about C value or C factor, that's where thickness comes into play. But again, the point of these definitions is strictly to get it across that R value, K factor, U factor, all of them are material characteristics. They are absolutes, and they have units of measurement. So how do you determine what a given material has for R value or K factor? Well, going to ASTM, which was formerly known as the American Society for Testing Materials, is now known as ASTM International. This organization has developed thousands upon thousands of standards and tests to show what these standards, to test for the values in these standards. And when you look into the ASTM guidebook, the most frequently test methods are ASTM C-177, ASTM C-518, and ASTM C-976. These are all very similar tests, and they are used to determine R value. The way they do this is they actually check for the K factor, so they're actually measuring the amount of heat that goes through any given material at a specific thickness. So if you take a look at the most widely accepted test, ASTM C-518, the scope of this test is to measure how much heat in units of measurement is being transferred through a given material, and it's done in a heat flow meter apparatus. And for everybody who's curious about what that looks like, it's basically a microwave size piece of machinery that has two plates in it, okay? And they take a sample of whatever you're trying to determine K factor on, and they take that sample, which is approximately 12-inch by 12-inch, flat, approximately 1-inch thick, and they put it into this little oven-looking device. The top plate comes down into intimate contact with the material, and the top plate is kept at a 40-degree difference from the bottom plate. One is hotter, one is colder. So obviously, heat is going to look to go to where there is no heat. So on both of these plates, in the center, there's a 6-inch by 6-inch sensor pad, and these sensor pads measure how much energy it is taking to keep the one plate cold and the one plate hot. And from those measurements, from those sensors, they can actually determine the quantity of heat that passed through that insulating material. And from that, you can then determine your K factor, and then you can determine your R value. So if you take a look at various materials that have been tested, you can see the correlation between these different materials, their K factor and their R value. And it's very obvious that the higher your K factor is, the lower your R value is. Again, the more conducive a material is to allow heat through it, the less it's rated in insulation value. Okay, so that's a pretty simple concept, and it's a straightforward way of measuring this material characteristic, this absolute. Now, if you go to different codes, whether they be voluntary or prescriptive, and you look at how these different codes describe R value or talk about insulation in general, they all refer to R value. For example, in California Mechanical Code 604.0, when they talk about insulation of ducts, they talk about R value and R value only. Moving on to Uniform Mechanical Code, they refer to Table E on pages 9 and 10, and if you go to that table, everything is described in terms of R value. Moving on to the International Mechanical Code in 604.7, when you identify insulation, it talks about the thermal resistance R value, and the all ducts insulation product R value shall be based on insulation only. This is a repetitive theme, and all of the codes that you're seeing talk about R value and R value only. Again, it's a dead horse I'm beating, but it's important to understand R value is an absolute. It has units of measurement. Now, moving on to the IECC, the International Energy Conservation Code. They have a very specific definition, and it is, as you see, thermal resistance, and it's, as you saw before, the inverse of the time rate of heat flow through a body. Blah, 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 blah. Okay, and you can see that in both imperial and metric, it has units of measurement. This IECC is written by ICC, who also writes IMC. That would be the International Code Council, who wrote International Mechanical Code, who wrote International Energy Conservation Code. And for those who may or may not know this, IMC, International Mechanical Code, has been adopted by all 50 states and the District of Columbia as their state code with some minor tweaking. But these definitions are all there. So if you take another look at IECC, you'll also see that they refer to the R value, that it should be determined in accordance with the U.S. Federal Trade Commission R value rule. Yes, there is an FTC R value rule, and it's in CFR Title 16, Part 460. Okay, the specific entry in federal regulations is CFR, for Code of Federal Regulations, Title 16, Part 460.5 for R value tests. And they are very specific about that. If you want to market a product that promotes a specific R value, then this product must be tested according to the following ASTM tests that we described before. And you can see that one of them is the ASTM C-518 test. This is not a code. This is not prescriptive or voluntary or suggested. This is federal law. They are stating that if you have a product that has insulation value and you want to market it, you must use one of these tests to prove that it has this particular R value. So that's how the most of the engineering world not only describes R value, but also tests for it and talks about it. So moving on, from time to time, there has been a discussion of a different type of test, talking about thermal distribution efficiency. And this is where things get a little muddy. They get a little foggy, and it's important to take a look at what this discussion is. So if you were to go to NSF, which used to stand for National Sanitation Foundation, they developed a protocol called the NSF P374 for air duct thermal efficiency performance. And this particular protocol looked to determine what the thermal distribution efficiency of air ducts were, especially when it pertains to buried ducts in the ground. Okay, you'll notice here that nowhere in the scope does it talk about R value. It specifically talks about TDE, thermal distribution efficiency. So what is this test comprised of? If you take a look at NSF protocol, it's a simple test where you have two troughs, approximately 10 foot long. Okay, that's all they are, 10 foot long. In trough number one, they want you to bury in sand a 10-inch diameter PVC pipe that is insulated with an insulation that has a known R10 insulation value. Okay, and how do they know that it has R10? Well, they did an ASTM C-518 test on it. That's how. In the second trough, you have your test duct or test pipe that you're looking to determine the thermal distribution efficiency on. So both of these ducts are attached to a furnace, a source of heat, and they blow 150-degree Fahrenheit air through both of these ducts for an hour. And they have temperature probes throughout the sand at the inlet of the two ducts and also at the outlet of the two ducts. So after that hour period, they measure the input and the output of the two ducts, and those temperature differences, if one exists, is your differential, your delta T, and that produces a ratio. If the ratio of your test pipe is within 10% of the control pipe, then it's said that the control pipe has the thermal distribution efficiency equal to that of the PVC pipe with R10 insulation. Now let that sink in for a minute, okay? What this basically is saying is that when you're blowing hot air through a duct, if it comes out hot, then your thermal distribution efficiency is the same as another duct that is doing the same thing, regardless of insulation. That's pretty much the equivalent of a hair dryer. So what they're saying is that because a hair dryer is hot in the back, it shoots out hot air. If this hair dryer were buried or insulated in the ground, it would have the same thermal distribution efficiency as that hair dryer that is not insulated. This really has nothing to do with R value. So in discussions with NSF and through our own studies, we took a product that's a commercially available product, and we actually had it tested per ASTM C-518. And again, this is measuring how much heat can pass through this particular material. So when this test was done by a third-party ICC accredited lab, it's called Radco out in Long Beach, California, it came back that this material had less than R1. Its K factor is very high, but yet when you take this same material and you put it through the NSF P374 protocol, it can be described by this protocol as having the thermal distribution efficiency equivalent to an R10. Okay, so that's something to be very, very cautious of. NSF P374 does not describe R value. It describes thermal efficiency or thermal distribution efficiency.
Okay, Jim, let me interrupt you quick. We got a couple of questions here to answer, if you don't mind.
Sure, go right ahead.
First off, seeing as how we're talking about round pipe, round things to check the insulation of, but you mentioned that the C-518 test was similar to like a microwave oven with flat plates on it. How would you test something that is round?
Well, you wouldn't, Brian, and that's actually a good question. The test is designed for flat materials, and that is how you're actually measuring the quantity of energy that's passing through that material. If you look at any point in a round duct and treat it in a bubble, look at it in a bubble, at that point, it essentially is flat, although it's surrounded by a plane of flatness next to it, and so on and so on and so on. So at any given point around that circle, you are dealing with a flat thickness of material, and at that point, the ASTM C-518 test describes how much heat can pass through that straight line point through that thickness of material.
Thank you, Jim. And one more question quick. Seeing here on this sheet that C-518 produces an R value of slightly less than 1, while the NSF P374 R10, is that a reliable ratio? Is there any way to compare the equivalency test results to the actual C-518 test results?
Yet again, another excellent question. And to be perfectly honest, Brian, I don't know the answer to that. I do know that you can take a material and compare it to R10 insulated pipe, and you will produce a thermal distribution efficiency that is equal with both pipes. It would be my opinion that if you were to insulate it to say R12 or R15, that you would get similar results. Again, think back to what the test is physically doing. You're shooting hot air down a very short section of duct that's buried in the sand. So in a sense, the sand is acting as an insulating barrier in addition to whatever may or may not be around a particular duct. So I do not think there's a direct correlation between R value and thermal distribution efficiency. So moving on, and as actually a good segue into my last statement there, we did have correspondence with NSF, and we directly asked the question. And Miss Jessica Evans, who is the Director of Standards Development for NSF, her statement to us was that the P374 test is not an equivalent to the ASTM C-518 for testing R value and is not a protocol that should be used to determine R value. Plain and simple, straight to the point, right from the horse's mouth. That's something that you need to be very conscious of as an engineer. If you're specifying a product and you're looking for an insulation value, you want to make sure that what you're specifying actually has insulation value and is not being marketed based on thermal distribution efficiency. So if you take a look at one state about such marketing practices, California, and all states have their own competition law. These states' unfair competition laws, they prevent unlawful, unfair, or fraudulent business acts. Okay, and there's many instances where companies have not portrayed their product with adequate information or deceiving information, and the penalties for it can be substantial. Okay, what we're pointing out here is based on all of the codes and the laws in the United States that if you're marketing a product using this NSFP protocol and you're using that protocol to state or infer that this product has a particular R value, well, then it might be and probably will be subject to an unfair competition law because it does not, should not, cannot be used to determine R value. Okay, now going back to our products, again, we offer single and double wall insulated products, and all of our products have been properly tested for C-518 test method for R value. And to reiterate our statements, the P374 protocol is not equivalent to the test that we use to test our products. It's not at all referenced in any of the codes that you saw today, whereas R value is. And more importantly, throw out all of the codes. Federal law prohibits the advertising of R value through ASTM. The advertising R values through NSF protocol. It must be through ASTM testing. Okay, so if you're the consumer, if you're the specifying engineer, you need to be very careful about what you're looking to purchase or have purchased to make sure that if you want an insulating product, that it actually has insulation value as per all of the current definitions and as per all of the current codes and as per all of the available regulations regarding that. So that would be the end of our quick webinar. I hope I got some information that is useful to people out there. If there are no other questions, I will turn this over back to Brian, and I thank you all for coming to us today.
Thank you, Jim, and thanks again to all our attendees. We know that in today's day and age, time is a very valuable asset, and we appreciate you taking the time to spend with us today. Please keep in mind all of our webinars are at 10 a.m. Central Time on the last Friday of the month. If you visit our website, www.fiberglass-duct.com, you can click on the Dig Deeper tab at the top of the page and click Webinars. All of these webinars that we have are always recorded, and we keep them on YouTube and link them to our website. You can also find the source capture webinars on www.monoxivent.com clicking on the Media Center tab and clicking Webinars. If any of you had any technical difficulties, if you had questions that just came to mind at a later date or you weren't able to get them submitted, please feel free to give us a call. Our number is 309-794-1000, and anyone from our support staff will be more than happy to help you out. Thanks again, and have a great weekend.